Welcome to an intro to triple integrals. The idea of a triple integral is really just an extension of a double integral. So let's start by reviewing what we know about a double integral. We said before that the limit as n approaches infinity of this infinite sum of f of x, y times delta a represents the double integral over the region R of f of x, y with respects to a. So this delta a here represented a small change in the area, which gave us differential a, and differential a could be expressed as dx dy or dy dx. So a small change in x times a small change in y, or we could express this as dy dx, resulting in the same small change of area. Well, for a triple integral, we have the limit as n approaches infinity of an infinite sum of f of x, y, z times a change in volume rather than a change in area. So this gives us a triple integral over a solid region V, where the small change in V or differential V can be expressed as dx, dy, dz, or any other combination of these three differentials. So a triple integral integrates over a three-dimensional region V, whereas in a double integral it integrates over a two-dimensional region, which we call R. And because triple integrals have three differentials, there are 6 possible orders of integration. In the next several videos, we'll be taking a look at how you can use triple integrals to determine volume of solids, as well as other applications. But on this video, we're going to focus on practicing evaluating triple integrals. And there's a couple things to mention before we do that. First, if f is continuous on a solid region V, defined by x, y, and z as we see here, and h1, h2, g1, and g2 are all continuous functions, then this triple integral over the solid region V of f of x, y, z with respects to V, expressed as we see here, where we integrate with respects to z first, and then second with respects to y, and then third with respects to x, the limits of integration of the innermost integral with respects to V must be functions of the outer limits of integration, or functions of x and y. And if we integrate with respects to y second, the limits of integration with respects to y must be expressed as functions of x. And then lastly, the limits of integration for x would be constants. Now all of these could be constants, which we'll see in just a minute, but if they are expressed in functions, and this is the order of integration, they must be expressed in this manner. Of course, if the order changes, because there are 6 possible orders, this would affect how these functions would be expressed in terms of x, y, and z. Let's go and take a look at our first example. Here we want to sketch the solid region of integration and then evaluate. Because we're integrating with respect to z first, z is going to be on the closed interval from 0 to 3, y will be on the closed interval from 0 to 4, and then x will be on the closed interval from 0 to 2. So the region of integration would be the box formed by these intervals. So notice in the xy plane we'd have a 2 by 4 rectangle, something like this. But then z is on the closed interval from 0 to 3, so it'd be all the way up to here. And so the region of integration would be the rectangular prism or the box formed here. So keep in mind this triple integral does not represent this volume. This volume is the region of integration. Let's go ahead and evaluate this. So we first integrate with respects to z, treating x and y as constants. So we'd have x, y, z squared over 2. Evaluate this at 0 and 3. Keeping in mind we're replacing z with 3 and 0. So when z is equal to 3, we're going to have 9xy over 2, or 9 halves xy. And then when z is 0, we'd have 0. Now we're going to integrate with respects to y. So we're going to have 9 halves xy to the second over 2. Now we'll replace y with 4 and 0. So when y is equal to 4, this will be 16, and divided by 4, that's 4, times 9, that's going to be 36x. And then when y is 0, this will all be 0. So we'll have 36x. And then lastly, we're integrate with respects to x. So give us 36 times x squared over 2. So when x is equal to 2, we'll have 4 divided by 2, that's 2, times 36, that's 72. And then when x is 0, this is 0. So the result is 72. Let's take a look at another example. Notice we first integrate with respect to z. So we'll have z squared over 2, or 1/2 z squared. We evaluate this, our limits of integration. This is nice, this is z squared, because when we sub in our upper limit of integration, we're just going to have 1/2 times y squared minus x squared. And then when z is 0, this will be 0. I think I'll go ahead and distribute the 1/2. Now we'll integrate with respect to x, treating y as a constant. So we're going to have 1/2 xy squared. Here we'll have minus 1/2 times x to the third over 3. It's important to remember that we're replacing x with y over 2 and 0. So when x is y over 2, here we're going to have y to the third over 4. Minus, we're going to have 1/2 times y over 2 cubed. That's going to be y cubed over 8. So we're going to have minus 1/2. This would be y cubed over 8 divided by 3 is going to be y cubed over 24. Let's go ahead and get a common denominator. Common denominator is going to be 48, so we'll multiply this by 12. So we'll have 12y cubed minus 1y cubed. That'll be 11y cubed. And let's go ahead and finish this on the next page. So if we integrate with respect to y, we're going to have 11/48 times y to the fourth over 4. So we're going to have 11 y to the fourth all over 48 times 4. It's going to be 192. So when y is equal to 2, we'll have 11 times 2 to the fourth all over 192 minus, and then when y is 0, we'd have 0. So I'll have 176 over 192, which simplifies to 11/12. And we'll have to stop here for this video. We'll take a look at another example of a triple integral in the next video.